Welcome to Code Corner. This is a video series we do at Mayfield Renewables where we like to talk about codes and standards as they relate to the solar and solar plus storage industries. Today, I'm going to focus in on the 2023 National Electrical Code and specifically Article 706 and 706.30A is the very specific thing I want to talk about today. And that is maximum rated current for a specific circuit. So for those of you that have been working in the solar industry, have been using Article 690 for a while, this really is similar to what we do in 690.8, where we are sizing the circuit currents for our different PV, parts of the different PV system, the different circuits there. So that's where we're gonna, that's kind of a correlation. You've been doing similar things before, and for our energy storage systems, this is where we're going to look at to help define what those maximum circuit currents are. So let's start off, let's look at the language in 706.30A to start off with. And what you'll see here is that we are using this section to figure out what the maximum current is for a specific circuit. And so we're going to use A1 through A5 to determine that current for those different circuits. And so I'll show you, you're looking at 1 here. We'll go through number 2 as well, and then we'll kind of talk through 3 through 5. But again, if you've been using Article 690, we're going to use this very similar. And the thing to take away from this is, just like in 690, this is going to define what our maximum current is. So this will tell us what the maximum value is on these different circuits. And from there, we're going to apply different safety factors or conditions of use, things like that. So you're going to be doing your D rates on top of these values. So first off, number 1, we're talking about the input side of the inverter. So the input from the batteries, and you can read through here and you can see that we are going to call the maximum circuit current is what the rated circuit is from on the nameplate or the listing. If you have a system where you have separate charge and discharge circuit ratings, then you're going to look at those individually. And if you are using the same terminals for both charging and discharging, whichever results in the larger current value is what you have to size your circuit for, which kind of makes some sense. If you have a single conductor connected to the batteries that's used for charging and discharging, which is really I've yet to see a system that doesn't do that, but they may be out there. If you're using a single set of conductors to go both charge and discharge, then you need to make sure that it's sized for whatever the largest amount of current is. And that's what this is telling us here. And so again, we do have a lot of systems where you may have different charge and discharge current values on the batteries, but again, we need to use whatever's the largest one. So still the same language here on this slide for number 1, and really just kind of pointing out here's where you're going to find that information. So in this case, we have a maximum charge and discharge current on this battery system, and you can see it's the same value in this case. So for this inverter from Solarc, we are not going to have anything different in terms of charge or discharge currents. So you're going to have to use that in this case 275 amps as the maximum current, as that's going to tell us what our maximum current is for our inverter input. So that would be what you'd use on to dictate what the conductor size is going to be for those conductors that you're connecting the inverter to. The other one to look at is this, and not the other one, the only other one, but the next one to look at is the inverter output circuit current. And so this in code reads pretty simply: the maximum current shall be the inverter continuous output current rating. So this is one historically maybe has caught some people up a little bit, because you can see here we've circled what that is for this specific inverter, but you do see other values there down below. So you actually see, maximum fault current, maximum pass-through current, things like that. And so what we need to be aware of is sizing our conductors properly and making sure that we're doing that right. But as far as the inverter output circuit current is, we're going to be using that value. Now there are some other values there. They talk about the inverter input circuit, making sure that we are calculating that. So if we need to calculate what that is, we need to make sure that the current is calculated by the rated power output divided by the lowest operating voltage that inverter can have on the DC side. So that would be a way of calculating that current if it's not given to us. And then we also need to be looking at number 4, talks about inverter utilization output circuit current, and same thing as that one I just talked about. So it's the output rating when the inverter is producing its rated power. So similar, very often you're going to get that listed as we're seeing here on the spec sheets. So those are, really the values you need to go look at in 706.30 and understanding how to properly size your conductors, what that current is that's going to be on those conductors themselves. All right, so that's going to be it for 706.30. We do have a lot of courses on our website that are available. It goes through different codes, National Electrical Code. We have a number of classes, International Fire Code. We have a lot of stuff around energy storage systems as well. So I encourage you to go take a look at those and see if there's some courses that we might be able to help you out with if you like this content. And then finally, always love to hear questions and comments. So if you have a question on this or other code corners or general questions, happy to have you reach out to us. If you have a suggestion for a future code corner, something that's come up, that's always helpful too, to just know what people are struggling with out there. So feel free to reach out, and we'd love to talk to you.